So that was what happened in the earlier example where I played only 10 games and I won 6 of them. In that situation, the p-value was something around 31%. And so that meant we have a 31% chance of observing our data from random chance alone. So that's too large for us to ignore. So we can't ignore the possibility that I am playing fairly and that I just happen to win 6 games out of 10 from random chance alone. Is that okay? Maybe, so maybe just okay. So when we do not reject the null hypothesis, okay, usually that means p-value is large, and we are stating that the results that we observe, the data that we observe, is a result of random chance alone. On the other hand, when we do reject the null hypothesis, usually the p-value is small, and we'll say the data we observed, okay, this is what we state. We are stating as a result of random chance plus the fact that the null hypothesis is wrong. Okay. So we're never eliminating the random element in our data. Okay, whenever we take random samples of something, there's always going to be a random element present. But when we reject the null hypothesis, we're stating that the null hypothesis is wrong, plus there's the random chance. Okay? Or in other words, random chance alone is not enough to explain the difference between what we observed and what we expected. Okay? Explain the discrepancy. What we would have expected. Okay. So let's go back to the t-test. In the t-test, we are comparing the means from two samples. So in the t-test, we have the null hypothesis, which states that the difference between the two population means is 0, so that there's no difference between the means of the two populations. And then the alternative says that there is a difference between the two population means. So if we assumed the null hypothesis is true, when we take two random samples, and calculate the sample means, what do we expect to see? We expect the two sample means to be equal, or about approximately equal, right? So, calculate the sample means. We expect the sample means to be approximately equal. Or I'll just say we expect to be equal. That is, we expect y bar 1 minus y bar 2 to equal 0. So basically, the null hypothesis is a statement about the population, and if we're assuming that to be true, then we expect our samples to reflect that. So if mu1 minus mu2 equals 0, mu is the population mean. You would expect the sample means y bar 1 and y bar 2 also to be equal. Okay. So we're expecting that. But what we observe, okay, may not necessarily be 0. Okay. So what we observe y bar 1 minus y bar 2 is probably not equal to 0. So if I take two samples, I'm probably going to get some kind of difference between the two samples, even if they're very close. Okay? And then the question now is the difference that we observe, whatever difference this is it statistically significant? Comes down to how big is this difference compared to the standard error. Okay. If it's much larger than the standard error, then it's probably significant. If it's not that much larger than the standard error, it probably isn't significant. Okay. We'll hold off on to that till next week, but I wanted to at least cover this introduction to Chapter 7 and hypothesis testing to get this ideas of p-values and all of that in your head. Okay, so just because I don't know, it's a meatier, heavier chapter, so I want to get this out of the way. Thanks for sticking around. I'll get your midterms graded by next week, and I'll send you guys a grade report. Yes, question?
So then, so you just have to do the lab from homework 5?
Yeah, so next week, the only thing that's due is the lab 2, okay, the one that was assigned last week.
Okay.
Okay.
And then the next one, covers and stuff or not?
Yeah, the no homework from chapter 7, okay. But review your notes once at least, so this concept of p-values and stuff